All right, you made it. Welcome to calculus. This is the last section of AB calculus, the volume of known cross sections. There are only 3 problems, so let's do them. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. So I'm going to attempt to draw this. I'm just going to warn you right now, it's not going to be great. Pyramids are a little tricky to draw. So I've got myself a pyramid, and there is a height somewhere in there, down the center, like that. And that height is 3 meters. It also has a square base with 3 meters. So this distance, not drawn to scale, clearly, 3 meters. Each cross section of the pyramid parallel to the base is a square. So think about that. If you were to cut cross sections, if you were to run this through our slicer, then you would be getting squares. So I'm adding up a bunch of squares. What is the size of each square? Well, each one is going to start off at 0 and eventually be 3, and they're just going to run all the way from 0 to 3. So let's just call it x dx. It's actually that simple. So when I integrate this, I get x cubed over 3 from 0 to 3, which is 27 thirds minus 0, which is 9 cubic meters. Of course, there is a formula for volume of a pyramid, which is 1/3 area of the base times height, which is 1/3. The area of the base is x squared. Sorry, this pen is not working today. 1/3 x squared, but we'll just go ahead and fill that in as 3 squared times 3, and we get 9. So there is a formula for it, but of course we're about to do 2 problems that don't have a formula so that you can check it. But pretty much what's happening is we're still just running things through a slicer from point A to point B, from 0, the sides are each 0 to 3. And as long as it's a known cross section, in this case squares, you can figure it out. So let's do number 2. A mathematician has a paperweight so that its base is the shape of the region between the x-axis and one arch of the curve y is equal to 2 sine of x. Each cross-section cut perpendicular to the x-axis, and hence to the xy plane, is a semicircle whose diameter runs from the x-axis to the curve. This is really hard to visualize, but we're going to do our best. So first, the base. I'm going to be drawing the base of the paperweight. It is just one arch of the curve y is equal to 2 sine of x. So I'd be going like that. This is going to reach a height of 2. This is the base of my, that didn't work. This is going to be the base of my paperweight. So let me just go ahead and fill that in. Nice blue here. So now here comes the tricky part. This is the base. And now I am going to build off of this base semicircles whose diameter runs from the x-axis to the curve. So here's the x-axis, there's the curve, and I'm going to build a semicircle like that. And then I'm going to build another semicircle like that. And then, so these are supposed to be coming out at you in 3D. It's really hard to draw. And I know some of you are thinking, there's no way I'm getting this. Okay, I understand that it's hard to draw. So remember, the sine curve is the base, and then sticking up into the air are these semicircles, and they keep getting bigger and bigger. So they start out really small. That's not sideways, it's sticking up into the air, and then they keep going up. Now, because this is so hard to visualize, I was fortunate enough to have a wonderful student named Brennan Carey make me a model of this on the 3D printer. So there you go. Normally in class, I would get to let you hold it and see it. All I could do this year was take a few pictures of it, but you can see the shape there of y is equal to 2 sine of x. And then on this, it's easier to see that on that base, he has built. Now, of course, he didn't make it solid because I wanted you to be able to see each of these semicircles and how they start out small and they keep getting bigger and bigger and bigger. And of course, if you covered it with something, paper mache or something, it would be a solid paperweight. But I purposely had him leave it open so that you could see what it looked like. So if you're going to run it through the slicer, then the volume is going to be the sum of all these different semicircles. So I'm going to add up semicircles. What is the area of a semicircle? Pi r squared over 2. And where am I going to start my slicer? I'm going to start my slicer at 0, and I'm going to go to pi, 0 to pi. But here's the tricky part, filling in this radius. As many of you know, I am an AP grader. I cannot stress enough how many people get this wrong. This is going to be the hardest part. You want the radius of your semicircle. The reason this is so challenging is because we have done so many problems now where you revolve something around the x-axis that the function height is the radius of a circle when you make that kind of revolution. But in this case, this radius is just this distance. It's not the height of the function. How is it related to the height of the function? It is half the height of the function. So the radius of each semicircle is 2 sine of x divided by 2. That's the full height, but that would be the diameter. And since I only want radius, I have to divide by 2. So the radius is going to be just sine of x. And like I said, this is where some people really start to struggle. So I can go ahead and take my pi out and my half out, and I do have sine squared x. This is so as if it wasn't a hard enough problem already, this is a challenging integral because you need to know the formula that sine, not cosine, that sine squared x is equal to 1/2 1 minus cosine of 2x. So that means I'm going to take out another 1/2. So now I have pi fourths, the integral from 0 to pi, of 1 minus cosine of 2x. So if you didn't know that identity, that's the only way, except you could just do the whole thing on your calculator. So my u is going to be 2x. My du is going to be 2 dx. So now I can rewrite this integral with, I don't have a 2 dx, so I'm going to add a 2 and then add a 1/2 on the outside, which gives me pi over 8 integral from 0 to pi of 1 minus u, sorry, not u, cosine of u du, as if this already wasn't twice a hard problem, first because it's cross sections, then because you needed to know this identity. Then on top of that, a lot of people go wrong on this next step. So here is another watch out, and that is that when you take the integral of 1, it's not x, it's u. You're doing everything with respect to u right now. So this becomes u minus the integral of negative cosine is negative sine, because the derivative of sine is cosine. And we're going to be going from 0 to, actually not yet. First I have to put my u back. So pi over 8, and this is why it had to be u and not x, is 2x minus sine of 2x. And I am going to be doing that from 0 to pi. So when I plug a pi in, pi eighths times 2 pi minus sine of 2 pi minus pi eighths, 0 minus sine of 2 times 0 is sine of 0, which is also 0. Like I said, we always plug 0 in because sometimes it actually is an answer. But sine of 2 pi is also 0, so this gives me 2 pi squared over 8, which I am going to type into my calculator because it's a little bit of an unusual value. So 2 pi squared divided by 8 is 2.467. And then my units, I believe linear units is in inches. So my volume would be in inches cubed. Or you could leave it as pi squared over 4. Okay, we only have one more. This solid lies between planes perpendicular to the x-axis at x is equal to -1 and 1. The cross sections perpendicular to the x-axis between the planes are squares whose diagonals run from the semicircle. I know you're overwhelmed already just reading it, right? Y, and then the other semicircle. So they were nice. They told you that it was a semicircle. We're only going to go from 1 to -1, so I can make this pretty big. And I am going to try to make my circle. Ooh, not good. Wow, I am so bad at that. So I want to make squares whose diagonals do this. Okay, so this is tricky. I'm actually going to go into space. So I'm going to leave this XY plane just like I did on the last one where this was the base and I built out of it. But I'm going to build not only on top of it, but also below it. This is just the diagonal of a square. So this diagonal is for some kind of a square where part of the square is above and then part of the square is below. I know, you're freaking out, right? This is really hard. So on this particular diagonal, there is a square running like that. And then underneath, there is another square. Okay, how many people did I lose? I have such good news. The next year, I had another lovely student named Ethan Stanley who was also willing to make a model on the 3D printer. And this is what it looks like. So I took a couple different pictures, again, since you're not in class and you can't actually hold it. But if this right here is the XY axis, you can see that it's a circle and that the diagonals of these squares, which are half above the axis and half below. And then this is just another picture so that maybe if you couldn't see this one correctly. But this is really what you want to know, that this is level, like your piece of paper, and then the squares are being built around those diagonals. So what are we adding up then? Remember, with volume, it's like you're putting this through a slicer. So if you started your slicer here, you're going to be adding up a bunch of squares, and squares are easy. You just need to know the side and then square it. So we want to know this side or that side. It's a square, so all four sides are the same. So going back to our original picture, which my other circle wasn't that great, so we'll try and make this one a little nicer. Remember that this distance is the square root of 1 minus x squared, and this distance is negative the square root of 1 minus x squared, and I'm trying to make squares, the other side of that square being over here, but I'm trying to find this value of x, and since it's a square, all four are the same. Oh, not x. We need to give it a different variable name. Let's call it S. So side, 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 side. So even though it doesn't look like it, these are right angles. So side squared plus side squared is equal to hypotenuse squared. And my hypotenuse is 2 square roots, right? If I add those two together. 2 square roots of 1 minus x squared squared. So not 4. 2s squared, there's going to be 4 on the other side. Already thinking ahead. 2s squared is 4 times 1 minus x squared. The 2 actually gets squared. The square of a square root just brings it back to where it was, which is going to give me s squared is equal to 2 times 1 minus x squared. So I'm still going to have a square root. S is equal to the square root of 2, 1 minus x squared. But I am going to square it. So since I want s squared anyway, I can rewrite this as s squared, which is 2 times 1 minus x squared. So I have to think about where my slicer is going to start and where it's going to end. I could say from -1 to 1, or I could double it and only go from 0 to 1. And as we've learned, it's really nice to plug in zeros. So my volume is going to be, I'm going to take that other 2 out, 4 times the integral from 0 to 1 of 1 minus x squared dx. Very tricky problem. If you want to go ahead and finish it on your own, it should come out to be 8/3, but I will do it super fast. 4 times x minus x cubed over 3 from 0 to 1. I put a 1 in, minus 1/3. When I put a 0 in, it cancels. So this is 4 minus 4/3. 4 is the same as 12/3 minus 4/3 is 8/3, which is the answer. All right, you have done it. You have completed AB calculus, and I hope you have a really great day.